Welcome to the next video in the mathematical logic sequence, still doing propositional logic. I'm only going to do one part of the section 1.5 on applications of the compactness theorem, in particular the part about filters and ultrafilters. To get started, we will be working throughout with a non-empty set I and its power set denoted with that fractor capital P in front of the I. So we will call a subset of the power set a filter on I if the following conditions hold. It is closed under intersections and supersets. I'm being very sort of fast and loose with my language when I say that, so definitely it is important to state this more rigorously. So if you take any two subsets of I, call them M and N, then certainly closure under intersection, that's very familiar, right? If you intersect them, it's already in F. Somewhat more importantly, if one is a superset of the other, then the superset must always be in F. Somewhat interestingly, this is equivalent to the single condition that the intersection is in F if and only if each one individually is in F. So a principal filter is one that is generated by some set, and we mean that to be the family of all supersets, right? So if you fix a K, which is a subset of I, we will call K a principal filter if that filter just is the collection of all of the supersets of K. It's stated more symbolically in the book, so if you want that, it's there. Okay, next, imagine that you had a filter which contained the empty set. Well, the closure under supersets would mean that every set, being a superset, would be in the filter, and then you would effectively have everything. So that's not an interesting filter, and therefore we say that a filter is a proper filter if it does not contain the empty set. Okay, so now for the definition that really matters. This one is going to be quite significant in a few of the future videos. The idea of an ultrafilter. So an ultrafilter is a filter such that for any given subset of I, call it M, precisely one of M or its complement is in the filter. Said another way, M is in the filter if and only if its complement is not. And it is worth just noting real quick that if you have a principal ultrafilter, then in fact it must be generated by just a single element. Finally, just real quick, let's define the notion of a cofinite set. So we say that M, which is some subset of I, is called cofinite if its complement is finite. So this is right. This is the finite complement property. And we call anything that has that property cofinite. And if an ultrafilter contains all of its cofinite subsets of I, then we call this ultrafilter non-trivial. Immediate from that is the fact that a trivial ultrafilter therefore contains at least one finite subset of I.